So today we're going to work on three problems, partially made up by myself, partially borrowed from AP tests that were released to the public. And these are meant to show some other things that could come up in polar where we're using some of the things that we've learned earlier in the year. So I would suggest at this point, since a part of it I'm going to use a graphing calculator, that if you've got a graphing calculator, take it out, and if you want to at certain points pause and try to do what I did on my calculator. I'll just kind of show you the results. I used a TI-84, so it's kind of hard to teach on a calculator because everybody uses so many different types of calculator. So anyway, this first one, we have a particle moving on this curve. This is a polar curve. What's different is, this is the first time we've talked something about a rate of change of the angle on a polar curve. So we know that the angle is getting bigger by 2 radians per second as it moves. And what we're trying to find is the speed of the particle at 0, 2. Well, this is a curved path, and the only way we've ever found of finding the speed on a curved path was in parametric. But we're in polar. But you have to realize these are all interconnected to each other. We have this relationship. X equals r cosine of theta, and y equals r sine of theta. And we know to find speed, we need to find dx dt and dy dt. Well, to start out with, since we have x as a function of theta, we can find dx d theta. That's a good starting point. So we go the first function times the derivative of the second plus the second function times the derivative of the first. And dy d theta, same way. The first times the derivative of the second plus the second times the derivative of the first. And what we'd like to find is dx d theta at this point right here, 0, 2. Well, we know at 0, 2, that's going to be when theta equals pi over 2. So when theta equals pi over 2, and what do we get? Well, r is 2. The sine of pi over 2 is 1, so you get negative 1. Ooh, we need r prime. So I haven't found r prime yet, but I can do that. R prime is dr d theta, which is 0 minus the sine of theta. So that means r prime at pi over 2 is going to be a negative 1, but the cosine of theta is just 0. So altogether, we have negative 2 for dx d theta at this point. And dy d theta at theta equals pi over 2, well, cosine is 0, r prime is negative 1, and the sine of pi over 2 is 1. So we have negative 1. Now how do I get dx dt when I have dx d theta? I can say dx dt equals dx d theta times d theta dt, and luckily we know d theta dt at all times t, which means at all values of theta it's 2. So we can just go negative 2 times 2, or negative 4. And we do the same thing over here. dy dt, theta equals pi over 2, is dy d theta times d theta dt, which is -1 times 2, or -2. So now I'm able to get the speed. Speed is the square root of dx dt squared plus dy dt squared. We're putting the x and y speeds together. So we get the square root of -4 squared plus -2 squared, or the square root of 20, or 2 times the square root of 5. I don't know the units in this figure, so I don't know. It's something per second. Now, I never did a graph on this, but could I do a graph what this looks like? When theta is 0, I get 3. When theta is pi over 2, I get 2. When theta is pi, I get 2 plus a -1. So I get 1 when I go out to pi, and then I am back here. So it kind of looks like I'm like that, and then I try to, so something like that. Now, the next part of the problem says to find the highest point on this curve. Well, that seems awfully easy. Isn't that the highest point there? So 2 would be the highest it could be, y equals 2. If our picture is right, it'd be right here where the slope is 0, where I stop increasing and start decreasing. But we just did this problem. Do we know anything about the slope right there? The slope is dy dx, which we learned in the last talk. That's dy d theta over dx d theta in polar. And we just found those two things out, -1 and -2. So it doesn't have a slope of 0. It has a slope of 1/2 right here. So it has a slope more like that. So maybe our picture is wrong. Maybe we should have gone up to some point up here and then come down. So that right here I have a slope of 1/2. And then I'd have a similar thing down here. A little rounded there. Well, in order to find the highest point, I guess we're going to have to do some calculus. Which means, how do we find highest? That sounds like a max-min problem. We're trying to maximize y. Well, we know what y is. It's r, which is 2 plus the cosine of theta, times the sine of theta. Now, without a calculator, I'd have to take the derivative, set it equal to 0 or undefined, find critical values. But I know this one doesn't work out really nicely as far as the angles and everything are concerned. So let's say we use the calculator on here. So what I'm going to do, I'm going to put this in y1 equals. And then in y2, another function, I'm going to take the derivative, however your calculator does it, and give it y1 as a function, and say you want to do it at all values of x. And then what it's going to do is it's going to graph the derivative. And graphing the derivative is so nice because it's going to give you the number line, basically. So what happens is, and it's important where you put your window. You went from 0 to 2 pi to complete that. So your window is going to be from 0 to 2 pi, the same thing that your number line is going to be. From 0 to 2 pi. And if you actually graph the derivative, in other words, turn the graph off for this. Leave it in there, but turn off the graphing of this. Sometimes you can do that just by unhighlighting the equal sign. You can on the TI-84. What you get, here's 2 pi and here's 0, you get something that looks like this. There's 2 places where the derivative is 0, and we can see the derivative goes from positive to negative to positive. So it really helps making the number line, and there's a way of getting, on all graphing calculators, of getting the zeros where that touches, and in this place it was at 1.196 and 5.087. So what I can see, this is y prime of theta. So now I know what y of theta is doing in this whole trip. It's going up, then it's going down, and then it goes back up. So the highest point is the biggest value of y has to happen at one of those 2 places. And I kind of already know at 2 pi, the sine of 2 pi is 0, so y is going to be 0. It's right there. So this is obviously the highest point right there at that many radians. And you can tell that's less than pi over 2. Pi over 2 is about 1.5 something radians. So less than pi over 2, that's the highest point. And if you want to get how high that is, all we have to do is then plug that back into here. So in your calculator, once you get that 0, you can store it, like in some letter A, and then you can just plug, back into y1 what A is. And it comes out to be 2.201. So yeah, this is 2 above the x-axis. This is 2.201. So kind of again, it went against what we were thinking when we first graphed that curve, but derivatives take care of things like that. So there's all these different variables and all different ways you can take derivatives. You can take dr d theta, you can take dy dx, you can take dx dt. All these things mean something a little bit different. I said in the last talk that we don't get slope by going dr d theta. Slope is always dy dx. But does dr d theta have some use, some meaning? So what if we take this point right here at 0, 2 and find what dr d theta is when theta equals pi over 2? Well, we've already found out that dr d theta is minus the sine of theta. So it's minus the sine of pi over 2, or -1. So what does that mean? It means as theta is getting bigger, as you go along the path, because that's negative, r is getting smaller. Which means since it's negative, the particle is moving closer to the pole. R is getting smaller, so it's getting closer to the pole. So right at this point, you can see the radius is 2 there, and as you keep going, it keeps getting closer to this pole. And just really quickly, what would it be at 3 pi over 2? Down here. At this time, you're going to get negative the sine of 3 pi over 2, or a positive 1. So at this point, as theta is getting bigger, r is getting larger. It's moving away from the pole. Okay, well, tell when the particle is moving closer to the x-axis. Now I wonder if we can think this out a little bit. If we have values of y that are positive, what's going to make it get closer to the axis? When the derivative dy d theta is negative. So I'm going to say when y is greater than 0 and dy d theta is negative. And then I can just look on here. I've got this right in this chart. So where is y positive? From 0 to pi. So during this time, y is positive. And where is the derivative negative? Right here. So from 1.196 to pi. Now, what's the other thing that could make it get closer to the x-axis? If y is down here and is negative, but now, as theta gets bigger, if y gets smaller. So when y is less than 0, which means from here to here, and y is getting larger. So it's a negative number, but y is getting larger, so it's moving closer. And that's going to happen where? From 5.087 to 2 pi. Now, does that go along with what we're thinking? Where is this first interval? From right here to right here at pi. And during this time, is it getting closer to the x-axis? Yes. And when's the other time? From right here, where we had the absolute minimum value of y, in that last interval up to 2 pi, you can see it's getting closer to the x-axis. And yes, you can see it just from the graph, but even if we didn't have a picture, if it was a more complicated thing, this logic would take us to the right intervals. Okay, so that's a pretty comprehensive problem. Okay, so we're going to switch over to one more area problem. So we've got r equals 3, which is a circle, but we're only looking at the semicircle. And we have this other figure, which is more complicated, this red shaped figure, which I let the graphing calculator do that. And we're only going from 0 to pi, that we're tracing out those graphs. And I want the area inside both of them. So that's going to be inside both of them right there. So, what do we know? The formula for area. 1/2 r squared d theta. Because we only need one radius, because this first section here, from 0 to pi over 2, all the slices of pi just go to the red curve. So I can just put in 3 minus 2 sine of 2 theta, if you leave yourself enough room. And you're going to go from where? From 0 to pi over 2, because that's all you have pi in that section. Then your pi changes. Once you get past pi over 2 to pi, then your slices of pi go just to the green curve. So then I could add 1/2 the integral from pi over 2 to pi, and now the radius is just 3. If you really want to do it all in calculus. I think you have to do the first part in. I think you can see that this second part is just quarter of a circle. So this second part right here, you could just go pi over 4 times the radius squared. So this way is more fun. This way is a little bit easier. They should give you the same answer. Now it says, from 0 to pi over 2, so we're just looking in the first quadrant, the distance between the curves. As you can see, the distance is changing. find the rate at which that distance is changing. So when you see rate, you think derivative. So that distance is a function of theta, and I want to take the derivative, so I'm going to come up with a variable. Call it anything you want. I'm calling it d for the distance, which is a function of theta. And what is that distance? It's this r value, the bigger one, 3, minus this other r value. And that can simplify 3 minus 3 into 2 sine of 2 theta. So now I can take the derivative. It's 2 times 2, or 4 times the cosine of 2 theta. So if I want to find it at pi over 3, it's 4 times the cosine of 2 pi over 3. Well, that happens to be negative 1/2. So you get negative 2. So, and that makes some sense that it's negative, because look at pi over 3, you're right here. Look at the distances. They are getting smaller between there. Okay, now, forget the green curve for a minute, and we just have an ant moving on the red curve, such that during this time, the ant is moving so that its angle is increasing at 3 radians per minute. And what do we want to find? dr dt. Well, we have r as a function of theta. So we can find dr d theta. But we want to find dr dt. So what do? We find dr d theta and multiply by d theta dt. So if we want to find it at a specific place when theta equals pi over 6, we can just go first, what is dr d theta? Well, we have to take the derivative. It's 0 minus 4 cosine of 2 theta. So you're going to get minus 4 times the cosine of pi over 3. And then we have to multiply by d theta dt, which we know is 3. So you get negative 12 times the cosine of pi over 3, you get negative 6. So what we're finding is dr dt at that particular theta, which would be pi over 6, would be right there. You would just say, well, we wouldn't go to the green, we would just go to red, that at that point in time, the radius is getting smaller. Starts out big and it's getting smaller at that point by this particular rate. So, some new things to learn in that problem. Okay, so I have one more here. This time I have a fairly complicated polar curve and a fairly easy one. 2 cosine of theta, we've done something very similar a few other times. We know that's just a circle. And again, we're only in the first quadrant here, so we're only going from 0 to pi over 2. So we only have part of the circle. And I'm going to take the graphing calculator's word for it, that this red curve is the other one. So what do I want to do? I want to find the shaded area, this region between these two curves. But I don't actually want to find it. I said there's a ray, theta equals k, that divides the shaded region into 2 equal parts. So something like that, so that this area down here is the same as this area up here. Looks like I'm off by a little bit, but I'll let the math do the work. How would you actually do that? Well, you'd want this bottom area to equal this top area. And we know how to do area. It's 1/2 the integral. And where are we going to go in this first? From theta equals 0 to theta equals k. So from 0 to k. And now our slices of pi, if you look at the slices of pi, they go between the two curves. We only want the part in here. So we have to go the big radius squared minus the little radius squared. So the big radius is this black one. So that's g of theta. So we'd have g of theta squared minus the little radius is f of theta. You could put in 2 cosine of theta in this if you wanted to, but as long as it's defined on there, I think that's good enough. And I want to do what? Set that equal to the same thing. And I'm not going to rewrite it because I don't have much room. But it would be the same thing when you're over here. It's still the slices of pi are between these two curves. But now you would go from k to pi over 2. So if you could solve that equation for k, it would tell you where that would go. Another way, in case some of you were thinking, is you could take all the way from 0 to pi over 2 and then just go from 0 to k and set it equal to 1/2 that total distance. It'd be doing basically the same thing. Okay, B, find the average distance between theta f of theta and theta g of theta. So taking a given, well, let's see. Taking a given value of theta and finding the average distance at different values. Like here, you're going to get a different distance depending on what your value of theta is. So how do I find the average distance? Well, this isn't a rate of change. It sounds like an average value of a function. So again, we have to make up our function. So I can call it d of theta. And what is d of theta? It's this r value minus this r value. So it would be g of theta minus f of theta. And you could put in what these are, but I'm probably going to use my calculator to do this. Now, what is the average value of that function? It's 1 over b minus a. Well, you're going from 0 to pi over 2. The integral from 0 to pi over 2, and what is the function? It's d of theta. D theta. And that turns out to be on your calculator, because you can put this into your calculator. You don't have to go to polar. You can just go to regular mode, regular rectangular functional mode, and just use x. There's nothing special about theta when you're doing an integral like this. And it turns out to be 0.485. So the average distance, if you took all these distances between, which get pretty small at the end, the average distance is 0.485. This looks like about the largest right there, which is 1. Now, in case I need that in the next problem, I could store that in A. If I don't end up needing it, then okay. Now it says, find the value of theta, where the distance between the two curves, which we know is what? It's d of theta, equals the average distance, which we just found out to be a. So that's the work we have to do. We have to set g of theta minus f of theta equal to a. So the easiest way to do this, if I have a calculator, is to call this y1. Or if you've already put y1 and y2, it could be y3. But anyway, somehow you want to put this function minus this function into a value of y, and then you can go to another value of y and just call it a, and just intersect those two curves. And when you do it, you're going to get a value of theta. And it turns out to be 0.517 radians, which is about a half a radian, about pi over 6, so you're close to 30 degrees. So somewhere around 30 degrees here, the distance here is equal to this average distance of 0.485. Now, I want to find the rate at which that distance is changing for the value of theta that we just found. So what you can do, you've already got this in y1, you can just take the derivative of that. So I can say derivative of y1, and you do it at 0.517 radians. And it turns out to be negative 0.581. So what does that mean? That means at this point right here, this is the rate at which this distance is getting smaller. So you can see it is getting smaller. In fact, it looks like it's getting smaller the whole time. So no matter what angle you put in there, you'd probably end up with a negative number. So I think these three problems give you a pretty good idea of what types of things you could be asked in a polar calculus question that bring into account some of the things that we've done in the past, plus what we've just learned in the last couple lectures. So good. Maybe we'll do one more day of problems tomorrow, and then we'll be pretty much done with the year. So thank you.